I'm Dr. Santosh Shah. In this video, we will talk about finding forces in cables subjected to uniformly distributed load. As the one you can see here, the Golden Gate Bridge in USA, is basically a parabolic cable subjected to uniformly distributed load. So such problems will be considered in this particular video. It is very important to know how much force is there in cables like this when they are subjected to uniformly distributed load. For considering the large span parabolic suspension bridge with a parabolic cable profile is very economical. So always we should know what is the maximum tension in the cable. This is one of the objective of this video. And why it is required, because if you see carefully the amount of force, tensile force, which is there in such cables is very large. This is a typical cross section of a San Francisco Oakland Bay suspension bridge in USA. So you can understand the cables like this, they carry very large force, and maximum tension is the key to know the required area. Let us quickly understand what are the properties of cable. Cables are considered to be the perfectly flexible and it is not extensible. That is one of the assumptions. Cables are flexible and they do not resist any shear force and any bending moment. There is no shear or bending moment resistance capacity in a cable. Cables are subjected to only tension force and it is subjected to acting tangential to the cable at any point. In case of parabolic or curved cable profile, we have to consider the tangent of the cable. So the important point to be noted here from this three concept is that cable can take only tension and no other kind of force. And weight of cable normally is ignored if it is very less, but cannot be ignored if the cable is very heavy. The cables they deform in a shape called funicular shape, meaning if there is a one load applied, then cable will deform in this particular shape. If 2 point loads are applied, it will take this shape, 3 and then this case. And if suppose there is a UDL, which is the case we are considering in this video, then it will be a perfectly parabola. This kind of shape of deformation of cable is called funicular shape. So let us consider cable subjected to uniform load, and the first case we will consider when the cables supports are at the same level. So same level like this, and this is called the span of the cable, and this is the horizontal thrust HH, vertical reaction at A, vertical reaction at B. This is called central deep or simply deep, and this is the point of the lowest point, and this is going to be the resultant tension is going to be maximum Tmax at the support, and this is going to be the uniformly distributed load on the cable. Let's consider that cable under the uniformly distributed load. Due to symmetry, we will see, since the support are at the same level, this V and VB is going to be going to resist the total load, that is W into L, and each reaction is going to be half, that is W into L by 2. So this is how we get the reaction directly, just by applying the condition of symmetry. In order to find this H, we have to take moments at point C0. In cable, moment at any point is 0, we know it. So since we know the deep here, let us take moment at C0. So when we set moment at C0 and considering the right hand side, we'll see that H into D, that is the clockwise, plus W L by 2, that is the total load, W into L by 2, and it is acting at L by 4. so that is moment due to this UDL. Then VB into L by 2 is negative anti-clockwise, should be 0. H into D into this is going to be W L square by 8 is equal to VB into L by 2. H into D, VB is WL by 2 if we substitute that, and finally when we solve this for H, we get a simple equation which has to be remembered for solving the problem is called WL square by 8D. W is the UDL, L is span square and divided by 8D, that is the horizontal thrust here. So VA VB WL by 2 and H WL square by 8D, these are the two important formula to be remembered. Cable tension at the ends, as we saw here, this is VA, this is H, VB, H, and this is a TA. So since VA, VB are same and H is also same, TA is equal to TB is going to be T max at the support, and it is given by root of VA square plus H square, root of WL by 2 whole square plus WL square by 8D whole square. This is what we got from the previous slide, both these relationships. And when we solve this, take WL by 2 out of this under root, we get WL by 2 into bracket 1 plus L square by 16D square. However, we can simply remember this T max is equal to root of VA square plus H square. Let us consider what is the minimum tension in the cable. Let us consider this right hand side first, and at some distance, at some angle theta, let's consider a point in between where the tangent T is the tensile force in the cable, and let us resolve that in two component. If at angle theta, this is going to be T cos theta. Okay, so when we apply sigma fx equal to 0, there is no horizontal force except T cos theta and H. So sigma f for x, sigma f 0, we must equate H equal to T cos theta, meaning the horizontal component of the cable tension at any point is equal to H. Okay, at any theta, if we take T cos theta, at any point horizontal component of the cable tension is always H, and it is going to be minimum at the center point. The minimum tension in the cable will be at point C, where your theta is 0, and T minimum is equal to H. This is to be remembered. The length of cable by equation of parabola, we can remember that the shape of the cable, the parabola shape is 4D by L square x into L minus x, and the formula to be remembered for length of cable is equal to L plus 8 by 3 D square by L if both our ends are at the same level. This is what we just considered, and if ends are at different level, let's say D1 and D2 above the lowest point and L1 L2 here, then the length of cable is given by L plus 2/3 D1 square by L1 square plus 2/3 D2 square by L2 square, where D1 D2 and L1 L2 are like this. Let us take a problem. Suspension cable having support at the same level has a span of 30 meter and maximum deep of 3 meter. The cable is loaded with a uniformly distributed load of 10 kN per meter throughout the length. Find the maximum and minimum tension in the cable. So this is the suspension cable, and the load is applied 10 kN per meter. This is the span and this is the central deep. We need to find out maximum and minimum tension in the cable. As we saw that VA is equal to VB is equal to WL by 2, 10 into 30 by 2, that is 150, that is VA and VB. H can be found by using the formula WL square by 8D. W is 10, L square is 30 square, 8 and 3 deep is 3 meter. So we get it as 375 kilonewton, and then maximum tension is T max under root of VA square plus H square, VA square 150 square plus 375 square is going to be 403.88 kilonewton, that is the T max, and we know T minimum will be at the lowest point and it is going to be H, that is 375 kilonewton. Let us solve one more problem in which a suspension cable of 100 meter span and 10-meter deep carries uniformly distributed load of 8 kN/meter over the full span. Find maximum and minimum tension in the cables. Also find the length of the cable. So the solution, if we see VA equal to VB WL by 2, 8 into 100 by 2, that is 400 kilonewton. H is WL square by 8D, W 800 square by 8 into 10 dip, so it's going to be 1000 kilonewton. Maximum tension Tmax root of VA square plus H square, 400 square plus 1000 square is 1077 kilonewton, and minimum tension is going to be at the lowest point C here is going to be H, that is equal to 1000 kilonewton. When you want to find the length of cable for both ends at the same level is given by L plus 8 by 3 d square by L. L is 100 plus 8 by 3 d square. D is the deep, that is 10 square, and L is 100. So it's basically 100 plus 8 by 3, that is 2.67. So 102.67 meter is the length of the cable. Now let's consider a uniformly loaded cable when the cables are supported at the different levels. So this is how a different level cable supported can be seen. D1, D2, maybe the different heights above the lowest supportive cable. Now in this kind of problem, how we can solve this? These unknowns are H, VA, VB, H, D1, D2 are given, L1, L2 to be found out from the center. So these unknowns can be solved by different condition. One of the condition is sigma Fy0, that is VA plus VB is equal to W into L, the total downward load, number one. L1 and L2, okay, there is the location of the lowest point from either support, L1, L2. However, the total length is going to be L, so this is another relationship. We can use it to solve the problem, taking moment at C from the left hand side, and same can be taken from the right hand side also to find few unknowns. And there is an important relationship for the UDLW. The deep Y is given by WL square by 2H. So D1 is WL1 square by 2H. Okay, L is the L1 here when this is D1, and D2 is WL2 square by 2H. So let us solve a problem based on this. Cables of a suspension bridge of 100 meter span are suspended from piers which are 12 meter and 6 meter respectively above the lowest point. If this is the lowest point and one pier is 12 meter above and another is 6 meter above, the load carried by each cable is 1 kN per meter, that is a UDL. Find the horizontal poles, that is the H in the cable at the pier, and maximum tension in the cable at the pier. Which is the maximum and what is H, we have to find out. So this is the given data. Let C be the lowest point of the cable located at L1, L2 from point A and B respectively, L1 and L2. So the condition first we can apply is sigma Fy0, that VA plus VB is equal to W into L, that is 1 into 100, that is 100. So VA plus VB equal to 100. Another is L1 plus L2 is L, so L1 plus L2 is equal to 100. Now using the relationship what we mentioned in the previous slide, that Y, that is the deep, is given by load into span square by 2H. So here when we take D1 is equal to W, that is 1. L1 square we don't know L1, so L1 square upon 2H, or H also we don't know. So 12 is equal to 1 into L1 square by 2H, that is H equal to L1 square by 24. Similarly for this side we can get is as 6 equal to 1 into L2 square by 2H, so H equal to L2 square by 12. We can equate this to H and we can get L1 square by 24 is equal to L2 square by 12, and we can say that L1 square by 24, now L2 is 100 minus L1, we can substitute by square by 12. This 100 minus L1 whole square can be written as 10,000 minus 200 L1 plus L1 square, and this 2 will come here as 2 L1, and when we take again this all the terms on the left hand side and make right hand side 0, we'll get this expression. And when we solve as a quadratic equation, and we get the root as L1 equal to 58.58 meter and L2 is 41.42 meter. Once we get L1, we can get L2 as 100 minus L1. Now since we want to find out what is H, we will take moment at C0 from the left side. So we can say VA into L1, that's a clockwise moment, minus H into D1, that is 12, minus W into L1 by 2, that is moment due to this UDL should be 0. So we get one relationship H equal to 4.88 VA minus 142.9. When we similarly take moment at C equal to 0, considering the right hand side, it's minus VB into L2 plus H into D2 plus W into L2 by 2. So when we solve this, we get H equal to 6.91 VB minus 142.9. This is equation 2. When we equate these two equations, we can solve for VA and VB, and again we can further put it in the above equation, and we can get H equal to 143.24. So once we get VA, we can see that out of VA and VB, VA is more, so the maximum tension is going to be at point A, because H is same. So T max is at A, that is root of VA square plus H square, that is 58.6 square plus 143.24 square, and that is going to be 154.75 kilonewton. And tension at B is under root of VB square plus H square, is going to be 149.10. As we can see, this is T max. Thank you.